So today we will continue our discussion on reinforcement learning, and today actually will be for the first time we will have an algorithm which would enable you to solve reinforcement learning problems. If you remember, last time we talked about Markov decision processes. So I will first start when I'm talking about reinforcement learning, reminding you what is Markov decision process. So in the case of Markov decision process, you remember we said that it's actually a quadruple of several sets. So one is the states, correct? It's the states which will represent our world. We would also have actions which the agent can take in this space, and also we will have transition probabilities. And we have here again to talk about the transition because we assume that our world is not deterministic. We're taking our action, we may be hoping to be in certain states, and there will be probability to end up in a state which we intended to go, but there also will be some chance that we will end up in a different state. So transition probability will actually look at a state we are starting with, at the actions that we are taking, and give probability distribution over all the outcome states. And finally, we will have a reward which tells us what brownie points do we get when we are taking our action from a given state, ending up in some following state. And the reason this particular representation was called Markov decision process, because we make an assumption that we made very strong independence assumption. And the idea is that whenever you, for instance, considering transition probability, the only thing that matters is the state you are in. It doesn't matter how you arrive, what you did before. Now the state you may end up after taking an action and the reward you are getting only depend on the state which encapsulates all the relevant history. So because of this degree of independence, this class of models are called Markov decision processes. So now, and last time, we look at several quantities that helped us to actually solve these Markov decision processes. First, we assumed that we know all of these sets, that it's provided to us, that we know it. And what we were interested in is to find a policy. And policy was just a function which for every state told us what is the action which is best to take. And what does it mean best? Is the action which results in the highest expected utility. You remember that again, because our state is non-deterministic, we don't know where we're going to end up, but our policy would specify to us, the best action we can take, that in the expectation the rewards that we're getting would be the maximal. And I demonstrated to you two algorithms, value iteration and Q-value iteration, that help you to find this policy. And I want just to bring to your mind one of the this qualities, Q-value. You remember that Q-value was a value of the state and a specific action, and it was recording what is the best expected value you can take if you start in state S, take action A, and from there on you act optimally. And our intuition was that we just wanted to quantify how good is a particular configuration. We know that we are really in a great space in the place where we're getting the reward, but there were a lot of kind of other states where you may not be getting any reward, but some of the states were very close, in some definition of close, to the place where you're getting the reward. It's almost where you want to be, and there are some states which are really bad. So the value function and the Q value was the one which was quantifying to us. And pretty much what these algorithms were doing, they were propagating information from these reward states to the rest of the board. And I want to remind you the connection between the policy and write you one of the Bellman equation which relates to Q value, because we will need it for reinforcement learning. And still, everything that I'm saying so far is all about MDPs. Okay, Markov decision process, where all these quantities are observed. So it would be useful for us, as I said earlier, to actually understand the connection between the quantities. So we can say that the best action you can take, how could you know what it is? It's actually argmax over QSA. So you will take your state S, for which you're trying to compute the policy, the next action, check what reward you can get if you're trying to go over all possible action and select the action which give you the maximal expected reward. So this is a relation between the policy, and we typically would use stars because they are optimal, and the Q value. Now I would like to introduce another equation which recursively defines the Qs. Okay, so the way we defined Qs, we said, now we took our action, okay, we don't know in which state we are going to end up. So that's why we have to consider all possible consequent states. So we'll try over all possible states. We say, what is my likelihood to end up in a certain state? And if I end up at certain state as prime, I am gonna now be taking some reward because I end up going to that state. You know, I will collect some reward on that way. Plus, we are having gamma, which is our discounting factor. And then what I would have written to you, I would have said plus the value of the state S prime. But what I want to do, because I want to write it all in the language of Qs, instead I would just write it's going to be maximum of Q S prime A prime over A prime. So what this quantity actually records, it say now we are looking, if we take maximum over all possible actions, it's A prime, that we can take, this actually gives us the value of the state. So I could have written to you, and that's what I've done in the past, I could have written you it as the value of state S prime. The reason I'm writing to you more explicitly is just because I want to keep it all at the language of Qs. But again, what this particular equation encodes is that the best value I can take from this state to the end is will be divided to two parts. The rewards that I am getting from taking just one step, this is the reward, plus whatever reward I can take from the following step multiplied by the discounting factor. And since we don't know in which state S prime we're going to end up, that's why we are averaging over all these possible states, multiplied by our likelihood, weighting by our likelihood that we are going to end up in particular S prime. So here I describe to you everything related to Markov decision process. And just to remind you, when we were talking about the Q value iteration algorithm, the way we computed it, we started with, let's say, everything initialized to 0. And then at each point, we will look at the Q values that we can compute for the number of step K. We assume that we computed it, and we'll move it to K plus 1. So kind of the recursion was on the number of steps, how many steps we can take until we compute the Q. So this is a very brief summary of the previous lecture. And now I want to start talking about reinforcement learning. Because clearly in the real world, and the interesting and fascinating problem where you can apply reinforcement learning, you never know all those values, okay? So what is logical for us to know here? Let's just write it here. So what is logical for us to know? You can say whenever I define my problem, I really need to know what are all the possible states. So we can assume that we know the set of states. We also know what are the actions that we can take in our world. So we know the actions because your agent have limited capacity of things they can do. Now, in terms of transition, you really don't know. You know, it will depend. And what we will assume here, that in reinforcement learning setup, we don't know ahead of time the table of all the transition. I mean, what you can do, you can try an action in the world and see what happens. And sometimes you will end up here, sometimes you will end up somewhere else. But the only way for you to know is actually to try. So we would assume that we don't know the T, the transition function explicitly, and that we don't know the reward function. And what I mean, I don't know what is the reward function. It's not like I never get rewards. I get rewards where I actually try and did something. I don't know a priori what are the good states in which I can get rewards. So we will assume that we have these tuples, states and action, and that we can experience different transitions. We can try them in the world and see where we end up and what kind of rewards we are getting. And in this setup, you see what now becomes an integral part of our estimation is actually acting in the world. You can try as much as you wish, and eventually you need to provide us with a policy. So how are we doing these trials, and what to try is an integral part of the computation. So what we will do today, we will talk about how to do Q value iteration algorithm in this new setup where experimenting in the world will be part of the computation. So let me start showing to you the first approach, which I will not necessarily take, but I will propose you this approach, and let's think together why it is not a good approach. So the first idea, you can say, okay, what I want to do, I want to end up in this state. Why? Because I already have algorithms for MDP. So why wouldn't I start by actually computing the transition and reward function directly? For instance, you would say, fine, I can take my agent, let the agent go in the world, you know, try, see where they end up, what rewards do they take, and then provide an estimate of T. So for instance, maybe you say, for me to estimate the transition going from state A, taking action A, and ending up in the state S prime, what I will do, I will just try some number of times to execute this transition. So you are going to go count how many times you actually end up going to the position S prime over all the other possible S primes when you started in S, took an action A, and end up in some S prime. So notice that here it's a specific S prime. Here we're summing up over all possible follow-up statements. So this will give you an estimate, and if you try enough times, you can assume that this empirical estimation would be close to the real transition probability. We can do a very similar thing with reward, and you can say, maybe if I just did it once, collected the reward, this is true reward. But like in life, you know, many times, you know, the estimations of reward are noisy. It doesn't have to be the same reward every single time just because the world, you know, is in fair place. And sometimes for the same thing, you get a huge price, sometimes you don't. And our measurements are, again, here noisy, so we can define. I'm just going to, you know, see how many times I went, collect all these rewards for this particular transition sequence, and then average them, okay? This is an option. So you can say we are gonna try it. So here we several times collected the reward, and then count as. So this is a number of times I transition from S with action A to state S prime, and for each one of this transition I just collected the reward and we take an average reward. So you can imagine here, here we'll say RT, and T goes from 1 to this count, to how many times you did the transition. We can write from 1 to this count. So it's very simple. Even the formula looks long, it's really very simple. We just say take the average of rewards that you've collected. Now, you can say, great, I collected this thing, and now I have my model. You know, I estimated T prime, I estimated R prime. Now I can just move myself from this world of RL, which has very high uncertainty, to the world of FDP and use Q-learning algorithm from there to get my policy. What is the big problem with this approach? And the big problem with this approach is the fact that, you remember I told you that the way, for instance, I am computing these quantities because I tried stuff in the world. Now, what actually happens? It's not like I can go back and forth and try, let me try it once, let me try it twice, let me try it 3 times. You took a step, now you're in a new step, and you're going to go somewhere else. And unless you actually get to certain state S, you cannot collect any information about it. And if you're doing some complex navigation task, your robot is very silly. At the beginning, the robot doesn't know where to go, and it will be maybe moving, you know, round and round in the beginning part of your route. It may never even get to the end point of the route because it doesn't know where it's supposed to come. So the point here, the main point here is that we need to make, in order to collect this information, in order to get reliable estimates, we need to get to some state S. And there is no guarantee that robots that tries randomly different things would ever even get there. And if your state is very complex, you would not collect enough statistics about some, how to get to states that all your estimate will be very, very noisy, and the resulting policies that you are learning will be insufficient for you to make intelligent decisions. So it's not enough for us just to take estimates. We are in some way need to inform the robot to which path it should be going, you know, to collect the measurements. And it's not a good idea just to say, okay, you go act, I'm going to collect the statistics and give you the policy. These 2 steps should be really integrated. And what we will do now, before I am going to explain you the algorithm, I just want to draw connections between 2 ways of thinking in this estimation process. One, and that what I demonstrated you here, it's called model-based reasoning. You kind of explicitly, you know, estimate all the parameters, you know, estimate your models through these parameters, and then you act in this world. Another way to say, you know, I don't need to have full estimates. I can go explore the world, collect some measurements, and as I collect the measurements, as I collect the samples, I become smarter and smarter, and it guides me to where to collect the samples. But to make it very simple, the distinction between the 2 ways of thinking, I will just draw you a very simple example that discriminates between model-based and model-free learning. So let's start first with model-based learning, and we will talk about a very simple thing that we're trying to estimate. Let's say you have some random variable x, and you are trying to estimate expected value. Okay, I would write it here. I would write it here what I'm trying to estimate. My goal is to estimate expected value, okay, of fx. So again, x is a random variable, there is some function f, and we want to estimate the expected value. So in this case, the expected value would be probability of x multiplied by fx. Okay? Now, in this case, In the case of model-based estimation, let's say I have k trials, okay? So what I can do, I can sample my random variables k times, okay? So I goes from 1 to k. So we can throw the coin, collect the numbers. So we're going to get k different numbers. And then, so I collected some values. And the next thing that I'm going to do now what I want to do is to give the estimate of px, correct? Because here you're throwing the coin gives you the number, and you want to know what is the likelihood of actually, and I'm drawing the hat because it's our estimation of specific px. I am going to say it will be count of x divided by k. So we will see how likely it is to observe this specific value, let's say value 10, in our k samples, and this will give you an estimate of this p hat x. It's very simple to what we've done here. And then I can say that my estimate of expected value is going to be what exactly we had before. Px fx. Okay, this is called model-based estimation. So now I am going to be doing something else. I will show you how you can make this estimation without ever explicitly estimating this value. So it's called model free. So I will start in a very similar way. I will sample the values of my x. So the first step is exactly the same step. But now, as I told you earlier, I don't want to estimate this p. So what I will do, I am going to do the following. Like this estimation, what it was capturing is how prevalent is second value. So let's say if certain value was 90% of the time there, that's how it was contributing to my final estimate. Instead of explicitly encapsulating it by, encapsulating it in 90%, what I will do, I will just sum them up. So each time when I get some sample, I compute fx of that sample. Okay, I sum them up when I goes from 1 to k, and I divide it all by 1k. So what happens here is that values of x which were much more prevalent would appear a lot, and they will contribute the number of times they appeared. We're going to add the f's to the sum, and those which are less prevalent are going to appear less. So we will take the sum and then divide it by k. So the estimate that we are going to get at the end will be the same no matter how we go, but we will see that when we are estimating the q value, this way of thinking would actually be very helpful for us. So with this idea in mind, we are ready to start thinking about sample-based estimation of q value for reinforcement learning. So now we are ready with this understanding of model-free approaches to talk about sampling based approach for Q learning. So I would just write, so we know where we are. We're talking about Q value iteration for RL, and it would look to you in some ways very similar, but also distinct from Q value iteration that we talked about in MDP. Similarly to the MDP algorithm with Q-value learning, we will be doing iterative algorithm, but now it will be based on the samples. And the idea here is this, because we don't know the transitions and rewards ahead of time, we will integrate the computation of the Q values with our acting in the world, meaning whatever we do in the world and whatever we experience, we want to take it and immediately update our Q values without waiting until the end. So we need to find a way to, first of all, to decide how are we acting in the world, to which action should I try even, and then if I already tried the action, how it's going to impact my estimation. So what I will do now, I would assume that I would tell you how to act, okay? So you would know what to try, but now our goal is to say, okay, if you try it and you get some evidence from the world, how is it going to change your cues? Once we've done and we finish the algorithm, then we will come back to discussion how actually to decide which actions to take, okay? So, as I told you earlier when we were talking about the sample-based way of thinking, we need to see what will happen when we are taking samples for our Q. So let's look at the formula that we wrote here before, which establishes recursive relation or relation between the Q value of one SA and then neighboring Q values. So this is the formula that we've seen last time from Bellman equations. And the reason we needed to have transition information, because you can see here that we just take average or weighted average over different states S prime. So when we are doing sampling, we will not know this transition function, but what we will do, we will start taking samples. So let's say I am now in my state S. I actually acted. What happened? In this case, since I acted, I will collect my reward that I experienced, and it could be, and I am going to end up in some new states S1 prime, correct? And then I am going to get discounted, add to it the discounted value of the state where I end up going. So in this case, as in the formula, and you may be thinking to yourself, what is this Q? At this point, I'm just establishing the relation. When we're doing estimation, let's say it's your previous estimate. We will come back to this point. But you agree that that is the value of the sample 1. We can continue taking samples, and let's say I am going to now take some sample K. I do it K times. So when we take the sample K, in this case, you are going to end up going maybe to some state S K prime plus gamma max A prime S K prime A prime. So you see this is exactly the same. You're just going to end up in some different state. Now what happens, I collected the K, these different K samples, and it's exactly what we've done previously in the model 3 learning. We can just take average over these samples. So let's write it down. So we can say that if I want to estimate my QSA, I am going to take an average of the values of all the samples where I goes from 1 to K. Okay? And I would write it to you now fully in the recursive form so that you can see it better. 1 K sum I from 1 to K. Okay, so it's just, you can see it's one of the samples. I just wrote it with I because we're indexing from 1 to K. Okay, so let's just see what is the relation between this formula, we're thinking in a sample-based way, and the formula that I wrote to you above. So let's look at the trivial example. Assume when I'm in state S, I have 50% likelihood to end up in state S1 prime and a 50% likelihood to end up in state 2 prime. So in the formula above, when I'm summing up, I will weight S1 prime with 0.5 and everything related to it, and everything related to S2 prime with 0.5. Here, we will not do that, but here what we will see is that among our case sample, roughly speaking, half times we're going to end up empirically in S1 prime and half times in S2 prime. So each one of them will contribute to the sum, roughly speaking, half of the times. So I don't actually need this estimate explicitly. I will collect it by just acting in the world, observing and getting similar estimates. So this is the formula for Q. And at this point, we could have ended up in saying, great, now we establish the recursive relation between neighboring states. We can do exactly the same algorithm that we've done for the case of MDP. However, there is a problem here. And what is the problem here? The problem here is that in reality, you cannot just go and try like we did, like throw a coin k times, because once you are in state S, you took action A, that's it. You cannot go back maybe. You have to continue moving wherever your algorithm takes. So we cannot really stay in some place and try to sample it 10 times, because there is a world, and world takes you to kind of unexpected places. You will come back eventually to this S, hopefully, and then you can improve your estimate. So what we don't want to happen, and this was our original idea, we don't want to have to wait until we can sample it all and then average. What we want to do, we want to do updates of our Q value each time when we get new sample, to do it incrementally. And that's why I'm going to introduce you a new notion which is called exponential running average, which is a way to do averaging, but which is different from the standard averaging that we are used to, because it weighs differently the significance of sample. It will give you more weight to the current sample from the prior samples that you've collected. So let me just show you here how this formula looks like, and then we will discuss why it actually makes sense to use this kind of formula in the context of reinforcement learning. Once I will do that, we will rewrite it. We write Q with exponential running average, and we're pretty much done. We can write the algorithm. But first, let me explain to you this notion of exponential running average. Okay? So pretty much what it does the following thing. It takes the current sample, so you see this is the notation that I would use for exponential running average. It takes the current measurement, the current sample, xn, then it takes the previous estimate, the previous measurement, multiplied by 1 minus alpha, where alpha is a number as usual from 0 to 1, xn minus 1 plus 1 minus alpha square sx minus 2 plus blah blah. And here we will normalize it by 1 plus 1 minus alpha plus 1 minus alpha squared plus blah blah. So this is the formula for the average, and it's actually easier to see it again in the recursive definition of exponential running average. We can write it in the following way. Xn equals alpha xn plus 1 minus alpha xn minus 1. I will draw it for you so you can see it better. So what it says, that the current exponential average is the sum of weighting of the current sample plus the weighting of the previous exponential running average. So it gives us a mechanism to take your prior estimate of, prior estimate of the running average and add to it the new sample that you are taking. So now we will take this exponential running average and add it and utilize this to compute differently our estimates for Q values. So what I would like to do now is, with this new understanding of exponential running average, to go back to our original question, is how we can recompute the Qs, but instead of using the standard average that I wrote, to do this exponential running average. And at this point I would also want to keep you back to what we actually want, is to reconcile different estimates, and I would start bringing back our notation about talking about Qs at the step I, or step I plus 1. So we can write now, with this definition, we can write now that Qi at the step I plus 1 as A, okay, is going to be equal alpha of sample, and I just don't want to mess up the formula, so I just write sample, plus 1 minus alpha of Qi as A. So this is our previous estimate of the value Q for state S and action A. So I multiply it by 1 minus alpha, and then I have alpha multiplied by sample. And sample will be one of those guys. So for instance, sample here, okay, will be R S A S prime plus gamma max A prime Q S prime A prime. Okay, so as you can see now, we have alpha multiplied by this expression plus 1 minus alpha Qi SA. And now we're in the position that we can do our normal estimation of the Q value iteration. As before, we will start and initialize everything to 0, and then we are going to iterate. So first we do initialization. I will do it like this. This is our algorithm. So the first step, as usual, is initialization. We will initialize all QSA to be 0 for all S and A. And then we are going to do our iteration, correct? We will iterate until convergence. And by convergence, we mean when the difference in values between two consecutive steps is significant, is substantially small. You can define how small you want it to be. And now let's look what happened at every step. So at every step, things that you do, and this is a difference from our previous Q value iteration algorithm, you actually are going to do a sample, correct? You're going to collect a sample. You're going to act in the world, do the acting. So collect sample, which would tell you S A S prime, R S S prime. So you actually acted up in the world and collected all the information. And the step 2b, we will just do exactly that. We're going to update our Q values based on what you observed. So we're going to write Q I plus 1 S A equals alpha multiply, and here I would write directly for you the whole sample. And what I see here, that I is missing, so I'm adding the I. R S A S prime plus gamma max A prime. So here I just plugged in the sample plus 1 minus alpha, sorry, 1 minus alpha Qi S A. Okay, let's just check the parens. So this is the first one, this is the second one. So if you notice here, we've done what we previously done when we expressed the value of I plus 1, our estimate at the step I plus 1, in terms of our Q estimate for the first I steps. And what I will do now, I will slightly rearrange for you this formula so that it would connect you to some other algorithms that you've seen in the past. We're actually done here. I'm just rewriting you an opening, closing parens that you can connect it to other pieces that we study in this class. So what we will do, we will put all the guys which are guided by alpha separately by the ones which are not. So we can write Qi SA plus lambda S prime plus S prime minus so you see that I separated all the term which are weighted by alpha and the term QISA which is not guided by alpha. So what I've done currently, if you're looking at this rewritten formula, you can actually see something which reminds you the stochastic gradient descent algorithm, where you have your prior estimate plus alpha and the update factor. It's just a different form of this update. And actually, we can demonstrate that the same conditions on alpha that we use to demonstrate convergence of the gradient descent algorithm are exactly the same that can be shown that apply here. So under this condition, this algorithm is guaranteed to converge. This is pretty much it. Once, what this algorithm will let you do, each time when you act in the world, you incorporate evidence and you incrementally improve the Qs. And when you are done, you can say, now I have my policy. Okay? The question that is lacking here, you can say, great. You wrote collect the sample. It assumes that somebody told me, you know, the state that I am in the state, fine. Which A should I be taking? Which actions should I be taking? Correct, we didn't discuss this issue at all. Which just says that if you are acting according to some policy, we will tell you how to incorporate the Qs. So the question is which policy? And here there is a notion that is very common in reinforcement learning. It's called, the question that we are talking about is exploration versus exploitation. Okay, exploitation here, it's not in a bad meaning of the word exploitation. Okay, so what does it mean? And it actually, I think, kind of relates to our humankind and different types of people. So one option for you is to say, you know what, whenever I'm collecting the sample, I'm just going to act randomly. I'm randomly going to select the A's and see what happens and continue this way. And this particular approach is called exploration because you don't have any predefined notion. You're just trying a lot of new things and seeing where are we going with it, correct? Now, the case of exploitation is the case to say, I already know something. Now, obviously, when I start, I don't know anything. But once I start kind of going around, and I want to remind you that the policy for the state is actually argmax, correct? Argmax over all these different QSAs. So you say, you know, I'm collecting the sample, I'm collecting the estimation of Qs. At each point, when I am updating my Qs, I am actually updating my policy, correct? So instead of just randomly strolling around, I am learning something from the policy, and I want to act based on what I already know. And if you're taking it to the extreme, you so much trust your prior knowledge, your prior experience, that you never try new crazy things. And there are people like that. They're very conservative and follow the same routine. On the other extreme is to do this exploration where you just don't care what happened in the past, I'm just going to try new stuff all the time. Like no institutional memory here. So what actually happens in reality, people combine the two. And what's reasonable to do is that at the beginning you know nothing, you can be exploring much more, but once you've been in the game for a while, you want to select action based on what you actually learned and do exploitation. And you can, this particular method is called epsilon greedy. So what this mechanism does, it changes epsilon as you continue. So epsilon tells you what is the likelihood of taking an action randomly. At the beginning, since you know nothing, you can act totally, this epsilon will have a high value, with high likelihood you're going to take random function. But as your Q values start to converge and to look a bit more realistic, you want to follow mostly them, but still have some likelihood to select a random action, so you're not fully committed to the policy, which is still, we're still updating it. So this is one mechanism of how you can combine this exploration and exploitation trend. And with this, we completed our material related to reinforcement learning.